Hello students. So today for class 9 we are going to start chapter 1, number systems. So the moment we hear the word number system, let us go back to the history of the numbers a bit. Okay. So when we are writing these things 1, 2, 3 and so on, what are these? These are these are numbers, right? Okay, but then these are also known as symbols. Symbol means, like for example, this represents k, this represents a, this represents r, this represents k. Okay, so these are different symbols in different languages. Similarly, 1, 2, 3, all these are different symbols to represent some number. Okay, the same thing in Roman numeral, it used to be written this way. Okay, so this is also symbol for 3, this is also symbol for 3. So we follow a number system. Okay, that number system has a name. Okay, and that number system has got 10 symbols. The 10 symbols are 0, 1, 2 till 9. Again, these symbols only are repeated and they become our number system. Okay, so this number system is given a name that is known as decimal. Okay, when we talk about computer language, in that case everything is in terms of binary, that is 0 and 1. So that number system will be known as binary. Okay, when we'll have only 8 symbols, then it will be known as octal system. When we'll have 16 symbols, it will be hexadecimal. So if it is 16 symbols, that means there should be 16 such symbols representing something unique. Okay, now let us come back to the number system, that is decimal system basically. So earlier we had the theory of counting. What is theory of counting? That suppose I have got one chocolate, you have got two chocolates, so total chocolates are 3. So that is theory of counting. So people used to represent numbers like this 1, 2, 3 and so on. So this was very difficult to actually replicate in other places. So that is why the most simplest form came up, that is the number system, the decimal number system actually. So let us dive into the details of this number system. Now, in this number system, uh, what do we have? 1, 2, 3, 4, and so on till infinite on the positive side. Okay. Now, I mentioned the word positive side. So, what does it mean? These numbers are known as natural numbers. Okay, natural number starts from 1 and there is a clear demarcation, 1 then 2 then 3 4. So these numbers are discrete in nature, as in like there is a gap between 1 and 2, 2 and 3 there is a gap, 3 and 4 there is a gap. Okay, so this is the natural number. Okay, it is represented by the symbol n. So if I am writing n in terms of mathematics, capital N, that means it's a natural number. Okay, a set of natural numbers. So now if I had suppose one chocolate and I ate away one chocolate, so what happens? It becomes 1 minus 1. So when I am using a subtraction operation, what happens? Does that number, the answer that I'm supposed to get, is it the part of this natural number system? No, there was no symbol as 0 over here. So that is why we had to expand the natural numbers. Okay, and that is how a new symbol got introduced to the natural numbers. And this new set including 0, it started being called whole number, represented by W. Okay, so we had natural number, then we had whole numbers, and then after that, suppose I had 5 chocolates and somebody asked me for 7 chocolates. Okay, so 5 minus 7. Now I already have 5 chocolates. That 5 chocolates I can give. What I can do is I can ask somebody else to give me 2 chocolates so that I can give it to this person. So how many chocolates I have? Minus 2, not 0. Why? Had somebody asked me for 5 chocolates, it would have been 5 minus 5, 0. But I am also asking somebody else. So I owe 2 chocolates to somebody. So how many chocolates I own? Minus 2 chocolates. That means in future, if I get 2 chocolates, I'm supposed to give those 2 chocolates to the person to whom I owe. So a new set of numbers got introduced. Okay, that is -1, -2, -3, and so on, along with 0, 1, 2, 3 on this side, and -1, -2 on this side. This was represented by the symbol Z, and these are known as integers. Okay, so integers include whole numbers and natural numbers. Whole numbers include natural numbers. Okay, even after that, suppose if I divide one integer by another integer, say if I divide 10 by 2, we get 5. It's already part of integers. That is perfectly okay. That is, it is inclusive in nature. But suppose if I do 7 divided by 2, 7 divided by 2, I know it's coming to 3.5, but 3.5 is not part of an integer. So these fractional numbers, okay, so they also need to be included. So that is how we get rational numbers. And rational numbers are represented by the letter Q. Okay. Now, apart from rational numbers, now let me talk a bit about rational numbers. What is rational number? Very simple answer. It is of the form P by Q, where Q is not equal to 0. Very simple. But then I want to add certain more things to it apart from the normal thing. Q should not be equal to 0, fine. Another thing, P and Q should be co-prime to each other. Co-prime to each other means, suppose I have got 10 by 15. So 10 can be written as what? 2 into 5. 15 can be written as 3 into 5. Now what are we getting? 5 is common to both, so I'll cut them off. 2 and 3, they cannot divide each other relatively. That is, there is no common factor between them. So with comparison to each other, they are prime to each other, and 2 and 3 are actually prime numbers also. Okay, so now this is in that stage, that is, they are co-prime to each other. Let us take another example. 21 by 28. So what do we get? 3 into 7, and here we get 4 into 7. So 3 by 4. 4 is not a prime number. 3 is a prime number, but 3 and 4 cannot cancel each other out further. There is no common factor in between them apart from 1. So they are co-prime to each other. So the rational number should be represented in a format where P and Q are co-prime to each other, and Q should not be equal to 0. Okay, so these are your rational numbers. Okay, now another set of numbers are still existing in the number system, that is irrational numbers. Now and they are represented by the letter P. I'll come to that, why P exactly. So now if I ask you what is irrational number, very simple answer. Numbers which are not rational numbers are irrational numbers. Very easy to say, but we must define it somehow, right? So let us delve into it further, that what exactly could be a rational and irrational number. Okay, let us take an example. 10 by 3. Does it qualify the definition of a rational number? P and Q are co-prime to each other. Q is not equal to 0. So it qualifies for the definition of a rational number. Okay. So there is another way by which we can say a fractional number is rational or not. We need to divide it. Okay. So 3, we are getting 1.333, it will keep on going. Okay. So whenever we divide the numerator by the denominator and the answer that we are going to get, okay, the quotient part is non-terminating means something that keeps on going. Like in this case it is 3.333, it keeps on going, it is never ending. So we represent such kind of numbers as 3.3 bar. So the point from which it is repeating, we put a bar for that. So we don't have to write 333 continuously. So for rational number, if it is non-terminating, that is same set of numbers are repeated, non-terminating. So it is a it's repetitive. So it is non-terminating because it keeps on going and the digits are repetitive. So these repetitive numbers are written 3 with a bar. Okay. Another condition is, or it's a or condition. So if I write 10 divided by say 5 or 10 divided by 25. Okay. So in this case 0.400 and gone. So that means in this case what happens? 0.4, it is terminating. So it also qualifies overall, obviously it will be co-prime in nature, so you can say it's 2 by 5. If you divide 2 by 5 you will get the same thing, that is 0.4. So for a rational number it has to be either repetitive, the quotient should be repetitive, or it should be terminating. So these are known as rational numbers. But in case if the quotient is not terminating and not repeating either, then those numbers are known as irrational numbers. Got it? Now I have a question. What is this? Very easy one. It's a pie. Not for eating, for solving mensuration based questions and other questions also. And what is the value for pi we know from class 8? 22 by 7, some say 3.14. As of now, let us take 22 by 7. So pi is equal to 22 by 7. Okay. Now, if we look at 22 by 7, take it from the definition from point of view of rational number. So, in this case, 22 and 7, they are co-prime to each other. Okay. 7 is not equal to 0. That means 22 by 7 is a rational number. Fine. Now pi if you look into details anywhere else, it's a irrational number. Okay, so here I am saying pi is a irrational number and 22 by 7 is a rational number. How can a rational number and irrational number be equal? Obviously it's a very genuine doubt or question. So one of my statement is wrong. Either pi cannot be a irrational number, or 22 by 7 cannot be a rational number, or pi cannot be equal to 22 by 7. We know for the fact 22 by 7 is rational number. We also know pi is a irrational number. That means first two statements cannot be proved to be wrong. Third one was pi is equal to 22 by 7. Okay, let us look into this statement. Equal to and equivalent. We represent equal to by this. That means they are equal. Okay, 4 by 2 is equal to 2. But when we are saying pi is equal to 22 by 7, it's wrong. It's equivalent. The closest approximate representation of the value of pi is 22 by 7. So pi is not equal to 22 by 7. It is equivalent to 22 by 7. Okay. So there is a difference between equivalent and equal. Got my point? Similarly, root 2. You must have seen this thing in class 8. If you have not, please go through it one more time, because this is very important portion that would be coming up later. So this is root 2. The value of root 2, if you try to calculate, it will come to 1.414, something like that. Okay. Now root 2 is a irrational number. Now 1.414, this is the closest approximation of root 2. Doesn't mean that 1.414 is the equal value for root 2. Similarly, 3.14 for pi is a closest approximation of pi. It is not the exact value. Okay. With modern computers available, the decimal places of pi has been found out till trillion. Okay, for calculative purposes. So definitely the actual representation is very difficult on a number line, but on number line it is, every point can be drawn. Okay, only thing is, because we are limited in finding the precise location, because the number is very huge. Okay, that is why it's difficult for us to represent. If we had those kind of precise tools, we could have represented it. Okay. Now let me ask you a question. Every whole number is a natural number. Every whole number means it includes 0 also. Okay, but is 0 a natural number? Of course no. So this statement is false. Now let us look at another statement. Every integer is a rational number. Of course it is true, because integers can be represented in the form, suppose integer is -7. So this can be represented as -7 by 1. 3 can be represented as 3 by 1. So this is of the form p by q, where q is not equal to 0. So this is perfectly okay. Now let us come to another portion, just a very short portion on rational number before exercise 1.1 from NCERT book. Now they are asking, insert 5 rational numbers between 3 and 4. Okay. So inserting 5 rational numbers between 3 and 4 means, what you will do, whatever numbers you are supposed to insert, you add 1 to it. So 5 plus 1 is 6. What we'll do? We will multiply and divide 3 with 6 by 6. 6 by 6 is 1 only. So we are not making any such changes. And this 4 will be multiplied and divided by 6. Okay. So what do we get? We get 18 by 6, and here we are getting 24 by 6. So between 18 by 6 and 24 by 6, we can write 19 by 6, 20 by 6, 21 by 6, and so on till 23 by 6. Let me write 22 by 6 also, otherwise you will say just for one number I'm making so much of thing. Okay, so we got the 5 rational numbers between 3 and 4. Okay, now similarly, if we are asked to write 5 rational numbers between say 3 by 5 and 4 by 5, how many rational numbers? 5. So 5 plus 1 is 6. What we'll do? 3 by 5 into 6 by 6 and 4 by 5 into 6 by 6. What will we get? We'll get 18 by 30, and here we are getting 24 by 30. Again same thing, 19 by 30 till 23 by 30. So these are the 5 rational numbers between them. Okay. And you should always remember there are infinitely many rational numbers between any two given rational numbers. So even if I were asked to put 100 rational numbers between 5 and 6, I could have done it. How? 100 plus 1, 101, again multiply and divide with 101, and you keep writing those 100 numbers between 5 and 6. Got it? Okay. So that is it for today. Next class or next video we are going to talk about irrational numbers. That would be the beginning foundation for exercise 1.2 onwards. Okay, so I hope you found this particular portion interesting, and from next class we'll try to also solve certain questions from the exercise also. Chapter 1 mainly doesn't have too many of numericals to solve, but lot of theory to understand that would be useful in class 10 also, because class 10 will have all these concepts revised again. So it's better to understand at this stage itself. At times it might feel little boring or little too easy, but nothing is too easy, nothing is difficult. It's just that the logical approach should be there to understand that, okay, like why this is happening, why that is not happening. For example, if I say 0 is a rational number, so you should be able to back it up with the example like 0 divided by 1. Here what is there? Q is not equal to 0. So it's a rational number. Okay. I'm not writing 0 by 0. So obviously this won't be a rational number for sure. Okay. So next class onwards we are going to see the irrational numbers, something which doesn't terminate also and something that doesn't reoccur also. Okay. Thank you for watching this video, and I hope you all like it, and do subscribe to it so that you get the notification for the next chapter. Thank you all.